Good morning. Thanks for sticking with us this late on a Friday. I know it's the last day and the party was last night, so thank you for coming to the session. My name is Lex Crosset, and I'm from AWS, and I'm here with two customer friends from Monsanto, Vishnu and Stuart. They'll be telling you about their use of EFS at Monsanto for big data applications. Really very interesting story. And in general, what I was going to do here is just spend about 10 minutes doing a high-speed overview of EFS. One thing I wondered is how many folks that are attending are actually EFS users? Did you have a show of hands? Just a few. Okay, good. So I'll do an overview. It's going to be relatively high speed. I'm going to touch on all the major points about EFS just to let you know what it is and how it works and what's available. And then the Monsanto team will tell you about their use case, which is very interesting. So the session is really intended for all levels, and I'll walk you through as much as I can in a brief period of time. And then if you would hold your questions to the end, we'll do an interactive Q&A session with all three of us in attendance. So we'll talk about EFS availability, scalability, durability, how it fits into our storage portfolio, what its key features are, and why those features matter. It is something different, so it's important to understand why you might use it and why, in fact, we'll talk about why Monsanto has decided to use it. So let's go through an overview. First off, our customers have taught us to think about cloud storage with kind of four major elements: file, object, block, and then batches and streams. And as you know, we just made some announcements, so the slides had to change with the addition of Snowball Edge and Snowmobile. Anybody take a look at Snowmobile, take a tour for Snowmobile? Yeah, very interesting. So AWS really is the gold standard for cloud storage, and when we look at the market, we see others who are offering storage as well, but the breadth of our offerings is really impressive, and we're going to talk about EFS in the upper left corner today, most of all, and it's important to understand that EFS adds a capable solution to the mix in that about 80% of storage in most organizations is file storage, which is kind of a surprise. If you didn't know that number, it's larger than you might think. So EFS very simply presents a file system where there is very little to manage, almost nothing. And when it's attached to an instance, it behaves just like any other file system. And it provides shared access to data across multiple EC2 instances, as many as a few to thousands. So it's fully managed by us. There's nothing you have to manage except to start to create it. It exposes a file system interface that looks just like standard operating system APIs for file systems. There's no file software layer to install. It's just like any other file system, and the access semantics are just the same as the operating system expects. And right now we're talking about Linux only, and in terms of EFS availability. It's designed to grow elastically to petabyte scale. It's kind of interesting when you actually run the command to look at the size of the drive that you've just created and mounted. You see a very large number. Sometimes folks look at that and say, well, that can't be right. Well, the answer is, it is right. It will grow elastically and shrink elastically as well. So it can be as big or as small as you'd like. It's very highly available and durable, and when you create a file system, it exists in 3 availability zones, and we'll talk about how that benefits you from a durability point of view. So why is this important? Well, operating file storage provisioning is kind of a pain today. You have to estimate demand, you have to think about growth of that demand, you have to procure hardware to provide for that growth, set aside space and power, rack it up, and then manage it. And generally, it's very easy to overbuy and to get into a refresh cycle where you're constantly issuing purchase orders. The idea behind EFS is to get away from all of that. It heavy lifting that's undifferentiated, and the lead times are not helpful when you run out or are about to run out of storage. You can obviously build your own elastic file system on the cloud, but it's a lot of work. You can either replicate EBS volumes with one per EC2 instance and mount all of them and manage them. You can use a shared file layer. You do need to set that up. Sometimes that can be complicated. And the cost of it includes both compute and storage. EFS kind of takes a different approach, which is to change the game. So really 3 ideas here: simple, elastic, and scalable, based on very highly durable and highly available design. So let's step into each of those. So EFS is completely managed by us. There's no hardware network or file layer for you to manage. You can create a file system in seconds. You basically just have to tell us what its name is and make one selection. It's compatible with NFS 4.1 on Linux, not on Windows. It is a very widespread file system that's been open and has been adopted at high levels. And it has a very coherent API and simple pricing. So it's elastic. It'll grow and shrink, so there's nothing to add or subtract, and you pay only for what you use, which is typical of Amazon services, but not typical of data center and other fixed storage systems. The price is simply 30 cents per gigabyte a month. So throughput and IOPS scale automatically with the amount of data you put on the file system. And you'll find that there are consistently low latencies with EFS, regardless of the type of file, whether it's many, many tens of thousands of very small files or the same number of very large files. You'll see the same kind of latency and throughput. And you'll also see us scale up on the back end to support thousands of concurrent NFS sessions. So, I'm sorry. Looks like I went the wrong way. It is a system that's designed to sustain AZ offline conditions. So when you mount an EFS file system, you mount it in 3 availability zones. If you lose an availability zone, you can continue to operate with the files stored in the file system, and therefore it's superior to traditional NAS availability models where you have to manage and fail over. It's very appropriate for production and tier 0 kinds of systems, and Monsanto will talk to you about that kind of system today. From a security point of view, just very high level, you can control traffic to EFS using traditional security groups and network ACLs, and you can also use POSIX file permissions just like you would using Linux anywhere. Administrative access can be controlled also with IAM, and if you federated to IAM, you can continue to use that level of federation to administer API access to EFS. Like all of our systems, it is, in fact, available via API in addition, in terms of administrative actions, in addition to being a file system that's mounted. You can use it in 3 regions today: West, East, and Ireland. And every file system or object that's written into the file system is replicated across 3 AZs in each of these regions. So a region that supports EFS must have 3 availability zones. Also important to understand the throughput model. As EFS gets bigger, you get more throughput available. And we know that workloads vary. One day you may be using lots of small files. The next day you may be writing tremendously large files. It really depends. The performance of the file system starts with a credit, but the overall throughput over time depends on how much data you're stored there, which generally meets most customer requirements. There is a burst model too that'll run for 12 hours a day, and it's really very straightforward. So if you take a 1 terabyte EFS file system, it can drive up to 50 megabytes per second continuously, or burst up to twice that for 12 hours a day. And that you start with a credit for that much, and as you scale up in terms of terabyte size, you'll get additional speed literally as a multiplication of 50 megabytes continuous or 100 megabytes per second burst mode. It's that simple. So there really are several different kinds of use cases that we see here, and they can go from high throughput and parallel I/O kinds of operations to low latency and serial I/O. You can see some of the examples that we've mentioned here. Some of them are massively parallelized that we see customers using. And the one we're here to talk to you today is a fairly diverse set of big data applications that Monsanto has implemented using EFS. So I'll stop now and hand this over to Vishnu and Stuart, and we'll again get back together again at the end and take your questions. Thank you.
Thank you, Lex. This is Vishnu. I lead the technical analytics platform for Monsanto. Been in IT for 15 years. I've led a lot of engineering teams throughout my career. Strong believer in talent. Look for A players. What I mean by that is a platform is vaporware without people. It's all about people. So hiring the right people, right talent is important and critical. Why am I at Monsanto? I believe in our strong commitment towards sustainable agriculture, being able to feed the world with billions of people, and being able to do top-flight engineering, being able to contribute to open source, being able to leverage open source technologies for our day in and day out business functionality. With that, I'll hand it over to Stuart. He'll run through the data platform, and then I'll hit the analytics platform.
Sweet. Thanks, Michelle. Hi, my name is Stuart Wong. I'm a platform solutions engineer at Monsanto. So that means at Monsanto, I get to design stuff, build and engineer stuff, get to play and mess with stuff, and provide support. So I've been in IT 15 years, held various roles, and I'm at Monsanto because I like to work with people who are very smart. Most at Monsanto are smarter than I am. And I also believe in the mission similar to Vishnu. And some of you may know Monsanto as an agricultural company, seed, chemicals, one of the best places to work, multicultural, if that isn't obvious right now, very diverse. But what you may not know is that our secret is that we use data with IT solutions. We build analytics, and that is truly how we work to gain valuable insight into the data that we have in order to help us on our mission to feed a growing planet. So what you can expect from this session is I'll give you some background as to where we're coming from, how we came to this place. I'll jump right into the geospatial use case that we're having. Then I'll hand over to Vishnu for his analytics. Please stick around for that because that's very deep. If you haven't figured it out yet. And then we'll do final thoughts, some recommendations, tips that we've accomplished with EFS, and then we can do some QA. So in about 2015, we embarked on our digital transformation cloud-first strategy. And what this meant was it wasn't a forklift for us. It meant that we were going to refactor existing applications. Say if there was a version upgrade, then we'd go into the cloud. Any new application or services would also be going into the cloud. And as you can imagine, the reasons for this are, they're plainly obvious up there. I won't read them all, but we had some issues around legacy and proprietary applications. We had scalability constraints, growth constraints. So just everything you can imagine that enterprise of our size would face. So in reviewing our portfolio, what we realized is that we needed to do a geospatial makeover. And up front, we wanted to have a couple things. We wanted to be based on open source technologies because that allowed us not just to be based upon open standards, but also agility to quickly contribute to the community at large, get stuff done that we needed to be done, not being held back by proprietary solutions and their timetable. We also needed a scalable, performant platform. our existing platform had constraints around scale and given the performance that we required. Obviously, we needed to be fault tolerant. This is a production system. It can't go down. We have a very wide portfolio that it needed to support. We also needed to be day one secured as well as easy, and there's a balance there that has to be maintained. You can't be so secure that you can't get anything done, but then if you can get anything done, then anybody can get in. So that needs to be important. And it also needed to be very cost effective. We're very conscious about costs, even though we see that it shouldn't be about cost first, it should be about value. So modernization, business agility, cost reduction. Now, at this point, I'm using some terms, and I just want to make sure that everybody who here knows what is geospatial when I say geospatial. All right, good. So, fair amount. So geospatial is, for those who don't know, is any data relating to location. And our portfolio in R&D is pretty wide. So spatial assets that we have include like weather, imagery, agronomics, soil, elevation, geopolitical, and so on. So we needed to support all of this on our various platforms. And these platforms include harvesters or combines. They drive out into the field using GPS coordinates, so it had to be, of course, accurate. Pretty much a farmer is just there, sitting down and having a tractor drive. Moving forward with traits, what's the next great discovery that will go forward? So the platform sustains that as well. It needed to be a common shared platform in order to support all these business functions. So initially, this is what we were thinking that the environment would look like, and this is high level. Obviously, it doesn't include everything that we have in our AWS account and our VPC. So it's pretty standard. Various AWS services, Route 53 for DNS, STS and two-factor authentication for security, IAM roles as well, CloudWatch for metrics and logs, CloudTrail, Elasticsearch, S3 buckets, that sort of thing. So the interesting things are CCAN, and CCAN is an open source data management system that we use for, or will use for this platform. For our spatial data portal. So it helps us to publish, share, find, and use our spatial assets. So that's pretty key. And so that connects to GeoServer. And GeoServer is an open source spatial application server. So that is actually where the data will be stored. Connecting to that as well is our data management system. We were thinking this would be just a giant EC2 instance that our developers can hit and get stuff done quickly. And you can see that there is a piece there, which is what we're here for. We needed some type of shared storage. This platform needed to scale, not just vertical, but also horizontal. So that meant auto-scaling group. It had to be clustered, active-active. So immediately, there's a shared component here that needed to be implemented. And also of note is that we needed RDS instance, Postgres with the PostGIS extension, because that supports spatial assets. So during our thoughts, our research, our testing, we quickly ran across a couple challenges around GeoServer clustering. There's no built-in clustering, so setup is also manual. Automation does help, but from what we saw, from what we did, it only took us so far. So since there's no built-in clustering or awareness of those instances, what we also saw is that a file-based data directory can lead to some corruption. Why is, as changes are made from one instance in GeoServer, it may not be seen by others because GeoServer does in-memory caching. It also doesn't share HTTP state across instances. So those are a couple of the challenges. We looked, most of the solutions were active-passive, and again, we needed active-active. So with some partnering with Boundless OG Systems, we found a clustering extension which solves a lot of these headaches. It handles detecting changes and broadcasting to cluster members via Hazelcast. So that took care of HTTP session sharing. It's also cleared out the cache. So that resolved those problems. But we still needed a shared file system. And of note is that for RDS, the reason why we went with RDS for our vector data is because that's more appropriate than, the reason why I went with EFS in this case for our raster data is because we thought that is a more appropriate use than a database instance. We're not going to be manipulating pixels, but we will be manipulating and changing points. And for those who don't know, raster is imagery data, so it's pixel-based. Vector data is points, coordinates, polygons. So what exactly did we compare? We compared database, and again, it wasn't the ideal solution for the shared storage, so I'm not going to go too much into that. But we also did bring your own comparison, or build your own, sorry, comparison to Amazon's Elastic File System. And so bearing in mind that there are solutions out there for S3 to share across, we didn't think that, again, that was a serious consideration here because those solutions are really not, they don't scale very well, they're not as stable. So that wasn't a consideration for us. It's a tool in your tool belt, but it's not the appropriate tool here. So let's jump into each of these. So in terms of setup, with bring your own solution, you have to make sure that you are going to do the orchestration, whether it be with Ansible, Salt, Chef, Puppet, whatever you want. You still have to do that configuration. With EFS, there's really minimal setup. And the two reasons why we actually didn't give this a 5 is because when we were doing it, it was in preview, and there was no CloudFormation. So, that's a ping against it. And then, but now there's CloudFormation, so it will probably get a 4.5. The next thing that we had against it was that there's still minimal setup to be done. It still has to be plugged into the servers in each availability zone, and you still had to do security group setup. So, it's fine. Now, the next category is management. How easy is the solution on a day-to-day basis to support? So with a build your own solution, you're going to be there with, your EBS attached to your EC2 instances, and then you have to manage the scaling of that, whether it be up or across, and you have to make sure that everything is set up properly in terms of metrics, alarms, login, all of that stuff. So we didn't like that. It's not that we aren't capable and we couldn't do all of that stuff, but you have to think about value. Where do you want to spend your time? We're already supporting a platform. We don't want to be supporting something else. And as Lex called out earlier, there is no management for EFS, so immediately that was where we were pretty on the bandwagon from there. The next thing is scalability. How easy does your solution scale out? And again, EFS scales as you go. It's usage-based, so that's a no-brainer right there. With a build-your-own solution, it will scale, but again, considering the management aspect of it, it's just not going to get the same level of rating that we gave EFS. And finally, performance. So this is interesting. Because the build your own solution gets a 5. And the reason why is because it's build your own. You can do as you please. You can get as exotic as you want with an in-memory file system that can give you as many IOPS as you want, as many megabytes as you want. So you can get as fancy as you want. So that's why build your own wins out here. It's not that EFS isn't fast, but you can always build it faster than EFS. Lastly is cost. With a build your own solution, it's going to be a bit costly, a lot costly based on how big we are and growing. So that's the middle of the road. You will always need to build and make sure that you maintain a certain threshold of file system, and then once you reach that certain threshold, then you have to then do the scalability. With EFS, the costing is based upon usage. It's, as Lex said, it's 30 cents. As you scale, you might find that you have some challenges around that. It's not perfect. Nothing is perfect, which, again, is why we don't give it a 5 here. But as you can see, EFS wins out handily here. So what exactly did we end up with? So this is our current, and by current, I mean a couple weeks old. This is not exactly what it looks like. We move pretty quick. But as you can see, there are 3 interesting areas where we decided that EFS was needed and we are using now. So for CCAN, our data management system, we are using EFS mount right there for configuration files, and this is just a couple megabytes. It's nothing big. It's not costing us anything. We also realized that for GeoServer's configuration files, we also needed shared storage. And again, this is a separate EFS mount that we're using. And the interesting area here is the data, the raster storage, where EFS is very big usage. This was, right now we're about 63 terabytes in production. Our non-prod is about 30 terabytes. We started off initially really quick, jumped up to 14 terabytes in a couple weeks, and our usage is a little spiky. So, and I'll get to this in the next slide, but we started off in terms of like benchmarking around 19 terabytes, and in about 3 weeks, we ramped up to 40, and that was 2 weeks back, and now we're up to 54. And I'm told that our usage is such that we can, at any point in time, just dump 80 terabytes in a couple days and move along. So it's going to be growing very, very quickly. So I'll give you an interesting story here. So you'll notice that there is a data pipeline going from EFS to our backup in S3. I would highly advise you to think about backup early. If you start off as we did at 19 terabytes and realize we probably should back this up, it will take you quite a while to do it. So I'd advise start the backup early, and it'll be fine. Right. So we also have a Lambda that gets triggered from S3 that does some processing when data is dumped in S3 and dumps it out to EFS. It does some image processing. Our standard format GeoTIFF is what we mostly use. Soil and elevation, curvature, those types of imagery is what really is stored on EFS. The average size is around 500 megabytes. It varies from kilobytes to gigabytes, but 500 megabytes is where we ingest from data pipeline, which is not on this, because again, we've moved on. From the data pipeline ingest as well as S3, we'll take in like 500 megabyte files, do some processing on them, and then result is gigabytes, terabytes of data. So that's how quickly everything is moving along. All right, so let's do some performance. What exactly are we seeing? And the takeaway here is that there are certain things that you need to be aware of when you're using EFS in terms of what you're going to be looking at. One of the things is your data read and write, as well as your metadata. As you can see here, we're not doing that much in terms of this period of time. There is a time limit that we have to get the graphs and everything in. So, looking at it now, it's a lot more because I looked at it before this presentation. But you need to look at your data read, write, and your metadata to see what kind of throughput you're getting, your client connections, how many clients are connecting. And you'll see 21B for bytes. Ignore that, it's 21 connections. It's just an issue with the graph. The next thing that you need to know, and Lex mentioned this, is that EFS, the performance is based upon usage. And so you are permitted, you have a permitted throughput is a throughput that you're permitted. And our average in this scenario is 2 gigabytes. However, as usage increases, you are allowed to burst up to a certain number. So there's a lot of room left on the table for us to burst into. And another quick tip here is when you're using EFS, for those who haven't already started using it, make sure that your monitoring solution, if you have something else not using CloudWatch, can actually read petabyte. We're using FileBeat, and that could not read. So for several hours, we were there just looking at failures and couldn't figure out why until it was painfully apparent that it just couldn't read petabyte. But CloudWatch can, and so if you have any challenges, just use the CloudWatch metrics, no problem. So this is a quick snapshot again of our usage. So percent IO limit is only going to show for those that are using the general performance mode. There are 2 modes, general and max. We're using general. If you're on max, you won't see the percent IO limit. And what this says is exactly how much are you using in terms of your IO limit. So if this is in and around consistently near 100%, you should switch to max IO. You are not very good candidate for general. Now, I'll tell you this, because I don't think Lex mentioned it. You can't switch from one mode to the next. You have to rebuild. And that's pretty much going to be stand up a new EFS use data pipeline to get them in sync and then flip over. It's not some kind of switch that you can just press. So just be aware, do your testing ahead of time. And the max IO is more useful for like big data, which is more the analytics side of the house if you want better throughput at the cost of some latency. And then total IO is just a combination of your read, your write, and your metadata reads. And this graph is cut because of they wanted us to put it on different graphs so everybody can see it. So that's why it's not on the same graph. But that's a combination of read, write, and metadata. So as you can see, we're doing about 18 gigabytes in this case on average. And with that, I'll turn it over to Vishnu, which will go into our analytics at scale and what we're doing on that side of the house. Thank you.
Thank you, Stuart. With the freedom to operate at Monsanto, that's us right there, Science at Scale Engineering. We have our own brand internally. I need to set some context here before we get into our use cases. One is being able to understand the breadth and depth in the analytics arena. In this journey in the last 1.5 years of going through this, the key aspects that we found was to first see the space, see the aspects of descriptive, diagnostic, going into predictive, prescriptive, and cognitive. Understanding that landscape, understanding the depth and breadth is critical as we started building this platform. And then the second aspect that comes along with it is being able to understand the persona. Who are you serving, right? Your data science community, your business analysts, your no-wise users. No-wise users just want to take their data sets and get base analytic out of it. Just simple, basic analytics, right? But then on the other side, you have data scientists who are looking at extreme geospatial analytics, looking at all the elevation data, soil data, things of that nature, and bringing it all together to derive insights. Then you have machine learning, and you have deep learning. So our platform supports the curve, focusing from the data scientists and moving forward towards the machine learning and moving backwards towards descriptive and diagnostic analytics. As part of understanding the depth and breadth, when we started building this platform a 1.5 years ago, we started doing a few lift and shift, right? Data scientists running their data science models on their desktops and laptops, trying to run them on a few fields. What I mean by a field is, as you're driving through the freeway, you see real fields of corn and soy. That's what I'm referring to here as fields. And then trying to predict based on those fields. They were able to do it up to like 10 or 15 fields, trying to validate their models, went up to 50, 70 a couple of years ago. Now, with our team and with our platform that we have built, we are moving towards doing it for a county, to a state, to the entire US. As part of doing that work, closely working with our data science teams, one thing became very evident: being able to think scale ahead. How can we think scale ahead rather than an afterthought so that we can bring our models and bring our data-driven products and reduce the time to market as we deliver them? So keeping that context in mind, we built our platform has two sides. One is being able to serve analytics as a service that our data scientists leverage, do their development in the cloud in our tech stack that we have built. And then from there, being able to take them to our production ecosystem where we run it at massive scale. So those are the two branches of our platform. So to keep the platforms intact and the general verbiage, what we have built and what we have called them as our non-prime and prime environments. This is for development, exploratory and discovery analytics at scale, being able to serve a whole bunch of tool stacks, being able to bring the IT out of our data science teams and let them focus on science, being able to provide them an infrastructure that they can utilize right out of the box. On a typical day, a new data scientist who joins our team at Monsanto, within an hour or two, they are onboarded in our platform. And depending on what they are trying to do, what problem they are trying to solve, they'll use one or the other or both. Non-prime is a shell-based environment. So in other words, I'm looking at exploratory analytics. I have a problem at hand. I don't know what tool I need to use to solve the problem, nor I don't know what data sets I need to use to solve the problem. How do we build an environment where they can focus on trying their own tool stacks without us being in the middle constantly? So that's non-prime. So it's already integrated with CLI, S3 access, Git CLI. All of those are pre-built in that ecosystem. All the configurations that we do, the user sessions, the backups that we take, the EMR configurations, it's pre-baked with EMR. So they can run Spark jobs directly from the non-prime environment. People trying to learn new technologies, trying to debug or dig into more into Theano, TensorFlow. This is their environment. Since they have pseudo access, they can pretty much try things out themselves. Since we provide them pseudo access, we also want to make sure that there is some governance with it. So we set up and tear them the whole environment out through AMIs. And Amazon provides this entire infrastructure for us to leverage from day one. And what is prime? Prime is more in scenarios where you know how you want to solve the problem. So there is a problem on hand. You have the data set. Now I'm writing an R model, or I'm writing a Python model. Having a UI-based tool stack like RStudio, like Jupyter, things of that nature, where you're just getting in, getting onboarded, interacting with your APIs, and starting to dig into your model, building your model, deploying it through our deployment pipeline, through our Jenkins pipeline, so you can test, and then pretty much release it out to our non-production environment where there is integration testing. So this is where our team comes into play. We work with our data scientists across the company, and we pretty much bring their models and enable them to run at scale. Then eventually it moves into our prod ecosystem. Going a little deeper into our ecosystem, it's extremely dense. We have been building it for a year. 2-week sprints, MVP cycles. Our data scientists have taught us a lot as part of this experience. We were able to understand all the different nuances or their pain points. IT comes from one side, data science from the other. How do we find that middle sweet spot? That's where we were getting to. And it has been a great experience. We learned a lot from it. As part of this ecosystem, as you can tell, EFS plays a huge role. And I'll be digging in further into non-prime and into prime as we go here. So this is our exploratory environment, right? Being able to leverage any tool stack, being able to play with the tool stack, being able to understand that this serves the purpose of the problem that you're trying to solve, and being able to leverage EFS along with it. All the different things, like I was sharing with EMR configurations, with ECS configurations, being able to take session backups so that they don't lose their current work that they are doing if crashes happen. Look, that's what happens in non-prime. And moving further into from the shell to a UI-based ecosystem, being able to utilize Sparkler from R, interactive debuggable Spark ecosystem from R-based environment, being able to serve R models through R workers on our computational pipelines, being able to leverage Jupyter for your Python development with TensorFlow baked in, with PySpark baked in. The configurations for all of them are on EFS. And we have leveraged that extensively now to the point where they can even go back few days or even months based on versions that we have provided with them for their sessions. Beyond their storage on S3, beyond their storage on datasets with EFS, beyond their code base in Git itself. That's our primary purpose in this space of utilizing EFS. And there is terabytes of data now, at least 8 terabytes across our user base. So trying to understand that culture, right? We can provide all the platform, all the tools, everything is out there, and as we are trying to bake this in, how do we get to the point of enabling our data scientists, learning from them, also helping them out, so that the time to market at the end of the day to produce data-driven products reduce? Now, thinking about IT as a whole, where we come in with 15 years of experience with hardcore talent, understanding our user base, building the capabilities for them based on the requests that are provided by them, right? So that we are not providing a platform for them saying that this is what you want to use. Rather, it's the other way around, where we work with them to understand what their needs are and then provide them through MVP cycles. Balancing freedom with governance. What I mean by there is, like the pseudo access, right? How do we tear the environment out so that if we do get compromised, that luxury is there, but at the same time, there is balance with it. Now, thinking about all the ISO best practices that we can bring in as part of our IT engineering experience. And then thinking about adoption. That's our adoption curve right now. We are on the late majority. We have close to 250 plus data scientists across the company, and around 203 people are leveraging our ecosystem today. So now, moving through that cycle, as you can see from doing our exploratory and discovery analytics, how do we get that to a production scale? I'm taking one of the use cases. We have several now running in our ecosystem. This is one of the most interesting ones, definitely out of it. This is our comparative advantage. Trying to understand where I can plant a seed in the ground, in a field, in Iowa, and understanding the environmental factors around it so that I can see if that hybrid can also perform well in Texas, in Minnesota, depending on where you're planting. And that's the bottom picture there, where you can see those little squares. That's the hybrid and ranking that hybrid based on the environmental factors. And be able to provide an advisor mechanism so that we can understand as a whole, as a company, on what things we can advise, what things we can predict and prescribe to our farmers. So identifying discrete zones within a field based on elevation data, soil data, weather data for years, bringing it all together through a spatial join, applying geo-k-means and multiple algorithms on top of it, and being able to suggest the classes for that hybrid in a specific location. And as part of that workflow, being able to advise, prescribe over a period of time, understand what the aspects are with it so that we can apply the right treatments for those plants. OK, so this is environmental classification running at scale. So what you see on the left is all the little dots. I'm sure you won't be able to see it all the way. But those are a number of fields where we started this experiment 6 months ago. We started looking at all our external cooperators, farmers, Monsanto as a whole, and being able to do the spatial join exercise by gridding them through as part of our provisioning cycle. So there is provisioning, there is model training, and then there is scoring. And as we started thinking about that and being able to provide the results, now with Amazon, with EFS, specifically being able to expand elastically, being able to serve that for the entire US. What does that look like? Being able to grid the entire United States. 94 billion polygons, 3 by 3 meter grids. That's what we have done. At each phase of the cycle, utilizing the data provisioning APIs, being able to take the APIs that Stuart's team have built as part of the data platform, and being able to serve them through our data transformation pipeline, understanding all the nuances that several people here know about the dot ties, all the different coordinates missing, WKT is not aligned properly, data cleansing issues, running through a QA/QC pipeline, and being able to run Spark on top of it for the clustering aspects, and then being able to serve the raster back to our geospatial platform so anybody can consume across the company. Being able to do this at scale means that generating the files that get served in between Avros and then moving into Parquets, getting them stored on EFS as a whole to get this use case done. So just to hit a note on performance, Stuart shared a few independently on the EFS use cases. This is doing that entire run, snapshots of it, obviously, with EFS and EMR. So what you see on the top is EFS as a whole, being able to see the writes, being able to see the reads, and what scale we are able to operate. And as it goes, as the data grows, the burst rates help out quite a bit with the increase. And then what you see in the bottom are the EMR snapshots of an R specifically. So thinking about discovery, thinking about exploratory, being able to do that work by our data scientists as they're building the models, being able to do that work in our ecosystem, and then productionizing it at scale has reduced our time to market significantly. Being able to take the entire ecosystem through, I just wanted to put this together so that you can see the grand vision. And this is exactly what we have today and expanding as newer use cases are coming in. Taking the data ingestion and transformation aspects, being able to leverage big data stack. You might have seen a few icons earlier. Now we leverage Cloudera for certain use cases where we see fit. We use EMR, we use EFS, we use S3, several services across. And this has helped us to accelerate our deliverables quite a bit. Amazon has been exponentially helpful for us. We also partner with Google. We also partner with our differentiators. What I mean by that is, what is the differentiator that is provided by a vendor? We utilize their strengths so that we can accelerate our time to market. Taking it up the chain, as you're looking at the collaborative data science environment, the discovery and exploratory environment that I was touching on earlier, how do we leverage that? How our data scientists leverage that, providing them training, helping them hands-on on several use cases so that they can understand and take their time to focus on science. And then taking it up the chain where we are actually productionizing them, thinking about cognitive, thinking about streaming, thinking about predictive, prescriptive, and historical analytics. On top of it, you might have also seen on one of the architecture diagrams I was sharing about Spotfire and Tableau being able to do BI discovery. That's also a part of the stack, and we are constantly expanding, looking at what's available in the market, looking at what is helpful for our business value, our business partners as a whole, and taking it forward through the chain. And all the outputs from our platform does get served through APIs and streams, so others can consume as well as part of that effort. So recommendations, trying to close the loop from the EFS perspective. Keeping it simple, we work very closely with Amazon, literally weekly calls as needed through Slack, multiple channels there. Choosing the appropriate mode for EFS, utilizing the general purpose versus max IO, when to use one versus the other, taking the right metrics at the right time so that you can actually see when it has to get moved up. Ensuring the tooling, Stuart touched on this earlier about file beat and looking at the metrics stack and seeing to collect the metrics wisely. Plan for redeployments. So this is interesting too, right? When you're deploying and setting up your clusters, your mount, unmount, right? That's a little thing, but you want to remember that as you're spinning up newer VPCs and sending new deployments out. Checking AWS limits. So this is more like a soft limit. I'm sure most of you have seen it. You get a 5 initially, and then you get a support to get in. Just remembering about it to do it. Backup and recovery, 70 terabytes, 80 terabytes, 90 terabytes as the data grows. You want to plan ahead. We learned it a little later, but we were able to catch up eventually. Performance model is more towards that appropriate mode as well. Very simple setup. Several of you have done EFS would know now that it's literally super simple to do. No management. What I mean by that is that amount of time and effort that we spend on IT and DevOps and whatnot, is that time well worth it for serving the business value? So you want to always have a balance between the two, right? You don't want to be spending too much time on DevOps, and then eventually months go in, and then there is no business value at the end of the day. EFS plays a huge role there because it's a managed service, similar to EMR. EMR plays a huge role there, right? And that's why we pick those services, so that we can get onto the problem, onto our critical challenges, rather than focusing on instrumenting all the time. Usage-based performance, we touched on that. Lex also touched on it. Based on how much you use, it's all pay as we go. And as you hit the burst rates, you get better performance based on the durability of EFS itself. Almost unlimited scale. There is a soft limit there. It's a 9 petabyte. And then you can send in a support ticket, and you'll get that expanded as well. At the end of the day, use EFS for its purpose. It's just a file system, but use it wisely. Thank you for being here for our presentation. We'll take any questions at this point.
Don't be shy.